Jules Verne back in 1870 had no idea that these words that he wrote, 20,000 leagues under the sea, would be prophetic. There are indeed considerable resources of these minerals down in the deep sea. What he didn't realize is they're not so easy to exploit. And so let's dive right into the topic. And this is what I hope to accomplish today. I've got a bunch of questions I hope to answer for you. First of all, what is deep sea mining? Has it started? Why is it coming? What are the types of deep sea mining? Where will deep sea mining occur? How will deep sea mining be done? Who's regulating deep sea mining? What are the environmental impacts and what has been done to minimize the impacts? So it's a lot of topics we got to go through, and hopefully I'll be able at least to give you a sort of a quick review of the topic. So first of all, what is deep sea mining? Mining basically is the extraction of minerals from anything. Yeah, I mean, if you were trying to get minerals from a tree, you'd be tree mining, if you will. For ocean and sea, there's sort of three basic types: seawater mining, which is actually extracting minerals directly from seawater, and you can think of sort of salt. Salt is one of these minerals that actually is extracted directly from seawater. Seabed mining is normally used, it's a term normally used for sort of shallower types of mining activities, it's shallower seafloors. And then deep sea mining is talking about very deep seafloor, 1,000 meters, all the way down to 5,000, 6,000 meters deep. So the topic today is deep sea mining. I'm not going to talk about the other two very much at all. Okay, so commercial scale deep sea mining is technically difficult. It is not started yet, although it's beginning. And I'll show you why I say it's beginning already. And the reason why it hasn't started, even though people have looked at it for decades, is because it's technically challenging. One of the biggest problems that the industry has to overcome is the pressure down in the deep sea. So in mining depths between 1,000 to 6,000 meters depth, you're talking about pressures in the area of about 2 tons to 4 tons per square inch of pressure, and coming up with equipment that will deal with that, and then figuring out how you can get things up to the surface from a mile, 2 miles down below the surface. It's not easy. Deep sea mining is not underground mining. Okay, it doesn't involve tunneling or anything like that. So just take that right off the bat. Make that clear right off the bat. Deep sea mining is more like strip mining, where you're removing surface material from the seafloor. And the mining industry hates these type of analogies, of course, because strip mining has a lot of negative connotations. But if the shoe fits, you gotta wear it. So, why is it coming? Because we're going to run out of terrestrial sources of these minerals in the near future. Probably not in our lifetime, but it's going to happen in the future. And people know that already, and people are already trying to prepare for when that happens. And meanwhile, as we're running lower and lower on our terrestrial sources of minerals, we're getting higher and higher demand as our technology develops.
What's that? What's that?
What's that?
That last picture.
I think that's a gold mine off of in Africa. But I just like the picture because whatever. Anyway, so there's a need to find alternate sources. So I gotta put it this way. This is the picture I use for most of my lectures because it's it's something that we don't always think about. But we live on a water world. I mean, 70% of our planet is deep sea. We think of land as what our planet's all about, but it isn't. If you're an alien and you come to this planet, you're going to go, oh, wow, it's a liquid world. And that's what it is. And so the deep sea floor, as it turns out, has huge, vast deposits of minerals. And these are not going to go ignored as we're slowly using up our minerals on land. And so that's why people are starting to turn to the sea. Oops, sorry, I got to point this way. So why are they all these minerals? Well, first of all, let me sort of try to convince you that there are a lot here. What basically happens is that minerals get sort of dissolved or get put into the seawater above the seafloor, and they precipitate out at different rates. And as a result of that, you can get a variety of sort of coatings on the rock in the deep sea. And to give you an idea, let's see if I can do this. This is sort of a graph that I've used a number of times, and this is particularly related to this manganese crust. Watch. That's in the slide. Sorry, I gave you some. If I can avoid pushing the next button here. Anyway, this is talking about this particular crust of this rock right here. And this is kind of an analysis of the elements that are found in this material. Okay, and what you want to look at, let's see if I can hold this here. If you look at this line, every single one of these minerals down here that has a dot above that line means that these minerals are enriched at a higher quantity on the seafloor than they are on land, on a normal crust. Okay, and that just shows you how many different types of minerals are sitting on the seafloor. And okay, some of these are absolutely crucial to our industry and our technology. And I don't expect you to read all of this. I just put this up because it just explains, like, copper. Everybody knows copper is absolutely valuable. There's silver, there's gold, zinc, manganese, cobalt, which is a big one for deep sea. Rare elements, tin, and many, many more are on the deep sea floor. Okay, in commercial extractive quantity. And they're used for so many purposes. This gives you another sort of graphic here. This is what's called a nodule, a different type of seafloor deposit here. And it's just an image that shows you manganese comes out of these nodules, which is used in steel production, cobalt for batteries, copper for wiring, of course, nickel for wind turbines, and high-tech kind of devices like this. And then this one here, I really like this because this shows you the amount of rare earth elements that are used in our modern electric cars. Okay, including all of these names, these weird little names, these are all rare elements. Okay, so so with that, you know, we need these minerals, we use them a lot. And so what is the forms that we can find on the deep sea floor? Well, there's three basic types of deposit. The first one is polymetallic sulfides that are also called massive seafloor sulfides as well. And these are the result of active hydrothermal bending, which means that there's very hot water coming up from the ground that's being heated by magma underneath the surface. And this water is carrying a lot of minerals in it. And these form up these called black smokers and they're white smokers. And then this material will precipitate out some distance from the actual bed itself. And when it precipitates out here, this is what they call sulfide deposit. It's material that's coating the rocks. This can get to even 100 meters more in depth, these deposits in some places. Another type here, this happens pretty quickly, and these are kind of young deposits because it's quite active. It's going on right now, but you're only going to find this type of deposit where there's active venting occurring, okay, and active volcanism. On the other hand, these two types of deposits are not. They're something where they are created over millions of years in a very slow process where minerals from just the overlying seawater precipitates out. In the case of nodules, it's like forming pearls. There's a little nucleus, a little shell, a little rock, something like that. And then minerals will precipitate on that, and that'll attract more minerals. And very slowly but surely, this builds up and forms these nodules that sit out on the sediment seafloor. And then this is kind of the same process, these cobalt-rich crusts, except that they form on any type of exposed rock down on the seafloor that doesn't get a lot of sedimentation on there. Again, these take millions of years to form, and they can get to be quite good. These nodules can get as big as maybe grapefruit or oranges. And for this crust right here, you can get them about maybe almost 20 centimeters in thickness, because they accumulate at a rate of about 2.5 millimeters per million years. So the older the seafloor, the thicker the deposit. Okay, this is gradually like this graphic, but it's only one that I can find here. This shows you sort of a general idea of the different depths that these deposits are found on. So for the cobalt crust, you're going to find these on seamounts, and seamounts are elevated above the rate or the main base distal seafloor as well. So these are kind of the shallower type of deposits, the crust here. And then massive sulfides are a little bit different. These are at 800 to 2,500 meters. Massive sulfides are generally around 1,000 to 4,000 meters in active volcanic areas, such as boundaries between different plates. And then your nodules are formed on the abyssal seafloor. You can also get them sometimes on the top of flat seamounts as well. But generally, they're down there 4,000 to 6,000 meters below the surface. Okay, so that's the depths. Now, where are they found? Well, this is sort of a generalized scheme showing where current knowledge has where these minerals can be found. So the blue are the polymetallic nodules. And so you can see quite a lot of areas around the world they suspect have got invaluable nodule. The sulfides, the polymetallic sulfides, as I mentioned, they require active volcanism, so they're all along plate boundaries here. That's why they're kind of like pearls on the screen all along here. And then your cobalt-rich crusts here are in yellow, and they tend to be, again, sort of older types of seafloor around the world. Okay, so where are these different types of mining going to begin? Because you've got all of these places all around the world, but where does it look like they're going to begin? Well, for polymetallic sulfides, this may change, but the initial site, which was being looked at back in 2012, was off of Papua New Guinea and also near Tonga as well. And it's Nautilus Minerals that was very interested in doing mining of the polymetallic sulfide deposits. So it's over here by Australia. And then this kind of shows you what it is. This is sort of an opened up chimney, one that's spewing up all of the smoke. If you were to cut it open and take a look at it, that's the result coming out. And these are all the mineral deposits that are forming this chimney that's inside of this area. And then if you look at this right here, that's what the massive sulfide deposit looks like outside of the chimney when it's set out onto the surface of the seafloor. It starts growing up. Doesn't look like much, but it's kind of goodies. Okay, how about manganese crust, cobalt-rich manganese crust? Okay, well, first thing I'll tell you is there's an area of the Pacific between Hawaii and the Marianas that's called the Prime Crust Zone. And the reason they call it the Prime Crust Zone is because a lot of the seamounts, there's tons of them in here, a lot of these seamounts tend to, because of their depth of their summits, tend to have a high amount of cobalt in the crust. And cobalt is one of those minerals that people are really got on about. I want to get cobalt, so there's many uses for it as well. So this is called Prime Crust Zone, and it's the richest crust on the planet. And the area that's being looked at right now is over here on the northwestern side of the Prime Crust Zone. So the reason for that is the Pacific plate is moving in the northwest direction. Okay, and the plate actually originated over the eastern side of the Pacific around the equator over millions and millions of years, about 100 million years. It's been migrating over toward the Asian plate, which is subducted right here, and there's the Asian plate as well. So that means that these seamounts that are all the way over here are the oldest seamounts in the Pacific, and this is where you're going to find the thickest crust. And so that's why that's a crust right there. That's just a piece of the salt, and that's not even a very thick one. It's just actually one of my specimens that I had. And then this is, I don't know if you can see this, but this is what a crust looks like on the seafloor. And when it starts to build up, it tends to get this sort of bubbly type of texture to it, which is called bacteroid. It's sort of referring to a grain-like texture to it. So that's one way you can sort of tell that you have a pretty thick crust, if you've got a lot of this lovely. But anyway, that's where it's most likely going to start. And then for the nodule mining, everybody on the planet is looking at the clearing factory zone. And this is southeast of Hawaii, right here. It's all in red. It seems like that's the best way to portray it right there. It's a huge area, 4,500,000 square kilometers here. And this is actually from the compiles. It's not from there. But anyway, that's where a lot of people are looking at nodule mining. And there's a number of reasons for that, mostly because the seawater between these two fracture zones is going to have a lot of minerals on it. So you actually get a faster accumulation of minerals in these nodules. And this is seafloor. How will deep sea mining be done? Well, they're not going to go down there and they're not going to start putting nodules in the pockets. Okay, they are building huge robots. And that's how it's going to be done. But I don't know if you can see this. That's a guy. Oh, that's a guy right there.
To scale.
Right there. These are all sort of cartoons by Nautilus Minerals who built these machines for their mining operations for the polymetallic sulfides. But as it turns out, this wasn't a pipe dream. They built it. Here they are. Now, the issue is that in 2019, we ran into some contractual and financing difficulties, and so it hasn't started yet. And we don't know what the status is at the moment, but these machines are there and they're waiting. Okay, this is Nautilus Minerals sort of cartoon of how they envision it's going to work. So there's three machines, and sorry, I want to move too fast there. The three machines are what they call an auxiliary cutter, a bolt cutter, and a collecting machine. And that's the first thing that happens, the second thing that happens, and the third thing that happens. So I will go through this here. So the auxiliary cutter, this guy right here, it goes down on these deposits that have got some topography and hills and so forth all around there. And this thing starts grinding away at all of these mounds of sulfide and starts making benches and leveling the surface and sort of breaking up the rock until it becomes sort of, I don't know what you call them, boulders or cobbles or something like that. And then once it's finished that, then it's followed by the bolt cutter. And the bolt cutter runs over all the sort of the tailings on these benches and starts grinding them up to a much smaller size. Okay, and so that's the second process of those. And then the third thing is the collecting machine. The collecting machine follows the bolt cutter and it harvests all of the tailings and it pumps it up to the ship, to the surface. That's how they envision this mine working. Okay, now for cobalt-rich manganese crust mining, I've never seen any machines developed for that. That's probably the hardest, perhaps the slowest type of mining that's going to come, which is a good thing, as I'll explain later. But I envision it's going to be somewhat similar, except you might not need this auxiliary cutter because these crusts are at most maybe 20 centimeters deep. So as long as they get the right terrain, the bolt cutter could probably run over and grind it up. And then either that machine would then shoot it to the surface or it would be followed by a collecting machine that'll suck up all the tailings and send it to the surface. So it'll be a pretty similar process to what Nautilus Minerals had envisioned. And now for the nodule mining, okay, well, the nodules are kind of like already broken up rock in the first place, right? So they don't need the auxiliary cutter, and they don't need the bolt cutter, they just need a collector and something to pump it up to the surface. And so that's all this machine does. It's like a Roomba that's running across the seafloor. Just except it's a little more regular than a Roomba. I don't think you can have running weirdly as a Roomba. But anyway, it's just going to harvest all of these and then shoot them up to the surface. Okay, and this is the easiest type of mining, and this may be the one that's going to happen first, that or the sulfide mining. Okay, is this thing happening? They built this machine. This is GSR, and I forgot what it stands for in the company, and they actually tested this machine, and they tested it without pumping anything to the surface. They were testing its collecting ability, and it worked. And then the last thing I read about this is it's supposed to head to the Clarion Clipper Extraction Zone in 2021, but I haven't heard that it actually arrived in this area yet. But this machine is built and it's ready to go.
Do you know who's building it? Is it China or America?
It's, what is GSR? It's a European company. Quite sure. Anyone else know? I should know, sorry. Okay, so who's regulating deep sea mining right now? Well, as most or all of you know, that every country in the world has the right to regulate their own seafloor out to their exclusive economic zone, which is 200 miles. And these are a coastline. Okay, and again, I don't expect you to read this, but I'm just telling you that this is a list of countries and companies that are planning to do some mining on the continental shelves. And normally the continental shelf is within some of these EEZ. So these are not international waters, and there's a bunch of different countries here and some companies. I brought this up because there's 3 of them on this list that are massive sulfide or polymetallic sulfide mines that are going to occur. This one right here, you can see that's the Nautilus Minerals one, and then there's a couple other ones as well. So this would be more like seabed mining rather than deep sea mining. But anyway, they are working, either the country itself is trying to develop the technology itself, or they're contracting some company to mine their water in their waters for some kind of profits. That's kind of the arrangement that Nautilus Minerals have, and they started a relationship with Papua New Guinea and with Tonga as well. And this has been a rocky road for them, this relationship, but that's how it works, where they get leases to actually do the mining in the country for a share of the profits. The country gets so much, and then they get so much for the whole thing. So that's an example of where the country itself is regulating what's happening in some waters. And then another example of that is here in Japan. This was, I think, last year, where the Japanese actually built this machine and are doing some testing of mining in their own waters as well. So given Japan has a lot more resources than Papua New Guinea, they can do this themselves. And I heard this was successful, but I was trying to figure out what they were mining. It was very cryptic, whether it was sulfides or nodules. This could be one of the two. Okay, but a lot of the deep sea mining activity is going to occur in international waters. Nobody has control over international waters. And so, or they didn't until a number of decades ago, when a lot of the countries in the world decided to create what's called the International Seabed Authority, okay, ISA. And this is based in Jamaica. And they just decided that Jamaica was the most neutral place to put this flag. Many countries of the world have ratified or bought into their authority to lease the seafloor in international water, except for one country. Anyone care to guess what country is not?
United States.
United States. But the United States companies are still getting in on the game, like Lockheed Martin is partnering with the British company to get in on the game as well. So anyway, that's the situation. It's a big body right here, as you can see, and it's a very important agency. It gets funding from all these countries as well. Come on. Oh no, I didn't. Sorry. Okay. So I'm going to go through who has gotten contracts from the ISA for the different types of mining. Okay, and right now this is the polymetallic sulfide mining. Right now the ISA is leasing plots along the mid-Atlantic ridge, in the Atlantic and in the Indian Ocean. And again, these are all fracture lines because this type of deposit requires active volcanism. So we're looking at, I can't even read this stuff here, so it's kind of either. Okay, China. Worse than the rest. China, Russia, France, South Korea, Germany, India, Poland. And I know in the Mid-Atlantic Ridge area, it's Poland, France, and Russia. And I think China, South Korea, and India have got these here. And I might have had one of those wrong as well. But you've got 6 countries that are already getting leases in international water to mine these massive sulfides. Okay, how about cobalt-rich manganese crusts? Okay, well, you got 5 countries right now. I'm showing only 4 of them here. These are in different colors: China, Japan, Brazil, Russia, and South Korea. And I'm not showing Brazil. That's over in the Atlantic, in a place that's off of Brazil, up in the national waters as well. And they're portrayed this way because, as I mentioned, this mining is going to occur on seamounts. And so these are all lease blocks that are located in different seamounts up in that northwest corner of the Pacific Ocean. Here's the Mariana Trench and the Mariana Sea right here as well, and the Japan's up here as well. So one thing you can't really see, if you were to zoom in on these sort of groupings of color there, you would see like a whole bunch of tiles ringing a lot of these seamounts. And each of these tiles is 5 meters by 5 kilometers by 5 kilometer lease blocks. And on each seamount, you might have 30 or more of these lease blocks for these different countries. And here's the problem, is that a lot of them, particularly China here, knows that the best area, the cleanest area on a lot of these seamounts are right around the edges. Okay, and that's why you sort of see them ringing these edges. It's really smart, but the problem is that that's where the animals like to be too. So, well, did I say something wrong? So how about nodules? Well, I mentioned nodules is the one that's the easiest to do. So a lot of people want to get into the nodule. I think it's total 13, well, there's some doubles in here. But anyway, there's a whole bunch of different countries, including China, United Kingdom, Cook Islands, Singapore, Belgium, Russia, Germany, all types of things. And then this shows you that Clarion-Clipperton fracture zone, which I showed you that's just southeast of Hawaii. It's all broken up into these various lease blocks of different countries and different companies. Now we're granted contracts for by the ISA. And I should point out these are exploration contracts from the ISA, which means they have the right to explore these resources within their lease blocks, with the possibility of then getting contracted to start extracting them in the future. And that's what's going on right now. These countries and the companies that are involved are actually sending robots or ROVs down to survey their plots and sample the quality of the nodules in their plots. Okay, so if that didn't convince you that deep-sea mining is coming, I don't know what will. They're building machines, they're leasing all over the seafloor. It's coming. Okay, so then let's turn to what are the environmental consequences of deep-sea mining.
Severe.
Okay, well, the first thing I want to begin with on this topic is the fact that if you look at a lot of these cartoons from the companies that are doing this, explaining what they want to do, a lot of these cartoons are missing a few things. Like they always show the seafloor as being barren. You know, it's just dirt, it's just rocks. See, that's all it's another here. Look at that totally barren, dark, nothing, you know, no problems whatsoever. Well, as it turns out, there are places on the DT floor that are like that. So here's barren sulfide area here. Here's a barren manganese crust area. Okay, so there are places that are barren. Okay, but the problem is that there are also places like this. Okay, this is some manganese crust. Sorry, I had another slide over here. Yeah, sorry. No, not too fast. Anyway, where they want to do the polymetallic sulfide mining, if there's still active venting going on, then there most likely are vent organisms in that area. And these organisms are extraordinary because they are so different than so many animals that are elsewhere in the world. They are not dependent on photosynthesis, they are dependent on chemosynthesis, right? They are getting their energy from chemosynthetic bacteria from the vents, okay? They're not getting it this way almost all the other animals in the world are getting their energy from. And so you get tube worms like this one up here that are spectacular, that are just absorbing a lot of these materials that they need. And then you can get these huge colonies around all these vents, and there can be tube worms, shellfish, weird crustaceans called the Getty crab, excuse me, weird octopi and fish, bivalves, you name it, that are just unique and extraordinary animals. Okay, when the venting stops, okay, then these animals typically die or move on. Okay, so massive sulfide deposits that are long dead may or may not be pretty safe to mine. Okay, but if there's any active vents around that area, then there's a real problem. Okay, cobalt-rich manganese crust. So this is an area where I've done a lot of work the last few years about and trying to document what animals exist on manganese crust. And these are some of our findings as well, that there are down there throughout the Pacific spectacular high-density deep-water coral and sponge communities that don't just have corals and sponges, they have all the associated fauna with crabs, sea stars, urchins, everything that are dependent upon these. These colonies up here, bamboo corals here, you would be standing about this high right here. These things are probably 10 to 15 feet high, massive, huge things. They're forests down here. And some of the sponges, I didn't have time to get to show you another place that we found last fall up in the northwest of Hawaii Island. But there were sponges that were literally probably 15 feet in diameter, just enormously old, huge animals that are living in very, very high densities. And if any mining were to occur anywhere near these communities, that's a real problem. And a lot of the species in these communities, we don't know who they are yet. We are discovering new species all the time. Okay, the second issue, the second environmental consequence, is a lot of these mining depictions don't show what happens to effluent. So you're pumping up water, and you're pumping in all the slurry, it's got all these minerals in it. You filter it out on the ship, then you've got to get rid of the water that you pumped up with the minerals. That's called the dewatering process. So you can have an effluent. Where are the effluent coming out of? So they don't seem to show any type of effluent. You also notice not a lot of sediment clouds being raised by any of these machines, these gigantic robots that are running across the seafloor. It's odd to me. So this is another depiction, which still I don't think is accurate. So this is a little more accurate. Of course, this is done by more of a conservation paper. But actually, you're going to get sediment plumes from the effluent coming out of the dewatering process. And you're also going to get sediment plumes down here on the bottom from the actual machines working the bottom. But what it doesn't show is it doesn't show the sediment clouds from the other type of mining, which there surely will be. Okay, so I made my own graphic. I actually paid a graphic artist to make this. And this is the way I think is more accurate. Where here you've got one of the robots, you actually have animals on the seafloor, on the crust, and they're all going to get wiped out, and be wiped out if they scrape off all this black crust off of the bottom. And in the process of doing that, they're sending out a big toxic sediment cloud, which is killing more animals that are down current. Why do I say it's toxic? Because this is going to have copper in it, which is poisonous to a lot of crustaceans. That's why they use copper and have found in ships, because the particles can go on your ship hull. Also, cobalt-rich manganese crusts have arsenic. So these are all going to be released in these sediment clouds. And then also, even up on top here, I think this is a more accurate depiction. They're not going to pump this water back down to where they did it. You realize you're going to pump against the pressure 4 tons of pressure. That's almost impossible. And I know for a fact that they're not going to do this because I worked as a consultant on a project for seawater air conditioning pipe off of Honolulu. And it never came to fruition. I did the ESA evaluation for the pipe route that they were going to use. The reason being is the state was requiring them to dump their effluent deeper than they could actually make it work economically, and so it was stopped. There's no way they're going to dump this effluent near the surface, as far as I'm concerned. And then that's going to be toxic to a lot of pelagic surface type of animals. Who knows what's going to happen? Okay. So what's being done about this potential wonderful industry, huge industry that could be catastrophic? Okay, well, first thing, nobody can care about, or people cannot care about something they don't know about. So the first thing you got to do is make people aware of the issues in the process. And that's what a lot of us are doing. We climbed up to the mountaintop and we're shouting from the mountaintop about this thing. And now, you've hardly heard a word about this years ago, maybe a decade ago. And now you can go on and see articles almost daily about deep sea mining. You can see this. Some of these deep sea mining environmental solutions, catastrophe, deep sea nodule mining, danger to the Pacific, push hundreds of species to extinction, right? History's largest mining operation is about to begin. So now people are starting to become aware of it. So step one. And then also, what's really nice is that David Attenborough got in on the game, and so did Sylvia Earle, two of the biggest names in nature and in marine science. And they're talking about this and doing videos. Sylvia's her Mission Blue, she's got articles on this, plus she can do talks about it as well. And then this thing came out about a month ago, and this is a very critical article about the ISA, talking about potential fraud and favoritism and everything else about the agency that's really the main controlling agency over this activity. So I don't know what's going to happen about that, but boy, it made some waves, and you might want to look that up and read that too. So very, very interesting. Governor Inslee signs a bill protecting marine waters from seabed mining in Washington state waters. Here's the problem. State waters are only 3 miles out. That's not very far out. I don't think there's too much mining going to go on in state waters, but hey, if somebody wants to mine in state waters in the future, they've got this obstacle in front of them. So anyway, Oregon's got the same thing in state waters. They've prohibited mining since 1991. Water. It's not a bad thing. It's just, there was one article about this that said it was curious why he did that. Okay, let's see. All right. What else is being done? Well, I'm going to talk a little bit more about what I've been doing, but other people have been doing different things as well. And I've been focusing mainly on manganese crust in the Pacific. And one of the things I've been doing for quite a few years now is supporting the U.S. mines in the Pacific. And in fact, in 2014, when President Obama was looking at expanding these original Pacific Node Islands marine monuments around the lake in Johnson Atoll, looked like this. There's only a 50-mile boundary around these, like Howland and Baker, and this is Palmyra and Kingman. This is Jarvis Island down here. But anyway, he wanted to expand them out to the full EEZ, which is the black border right there. And I was actually asked to review that submission, the material on that, and I reviewed it. And a lot of their argument is about sharks and turtles and seabirds. And my whole point was, well, no, that's not a big deal because all the data says that the seabirds aren't going to get that far out. So that's kind of a weak argument, but your main argument is mining. And they went with it. In fact, I even heard it on the news broadcast about mining. It was one of those moments where my wife was there, like, hey, I told him to say that. I told him. Anyway, these two got expanded out way from Johnson to the full EEZ. This one did not. There's too much of a fishing lobby going on for this one. But now there is a move to try to push this out to the full EEZ. Jarvis got protected as well. I'm not sure this is what we needed. There's not that many seamounts down here. But anyway, I've been supporting all these monuments. We've done a lot of survey work in monuments, and I also supported the expansion of the Papua now with the National Monument as well. I would support this if it's out because these are all in the Prime Crust Zone, and I would love to see if the Marietta College National Monument got expanded out to EEC as well. And that's all the U.S. can do is own waters to protect against this industry. But that's some got some areas. Okay. One of the biggest problems you see in a lot of the articles is that nobody knows what's down there. It's been so poorly surveyed. So for 2 years, from 2015 to 2017, I was contracted to be the science lead advisor of the Oceanography Explorer Capstone campaign in the Pacific. And we went everywhere. American Samoa, Johnston, Wake, Howland, Baker, Mariana Trench, everywhere. And a lot of the ROV dives, we had a remotely operated vehicle. A lot of those dives were done on main crust communities. And so we got hundreds of dives in on that type of habitat and that type of surface and looking at all of the different animals that were living there. But we didn't leave it at that. So sometimes this type of video just winds up on the shelf and nobody looks at it for years. Instead, we set up a lab the University of Hawaii, an annotation, video annotation lab with the assistance of the Monterey Bay Aquarium Research Institute, because they had the best software for annotating deepwater dive video of anybody. And they annotated all of those dives, excruciatingly detailed, 73 fields in this database right here. How many animals? What's the animal? The full taxonomy. How many were there? How big were the animals? What animals were associated with those animals? What substrate were the animals on? The depths, the positions, everything. Hundreds of thousands of records were created in this big database, which from every single thing that we could get out of this video, we got it out of the video. And then we submitted all those records to the NOAA Deep Sea Coral Research and Technology Program. They're now incorporated in their online database and are available to anyone in the world. They can extract them and analyze them and have at it and do whatever you want to do with these records. They're all in it now, and there's millions of records because a lot of people are contributing around the world to this database. It's become the biggest database of deepwater corals in the world right now. A lot of our data is right here. And so we're getting information, we're getting a lot of information that'll help determine where do these amazing communities form, how do they form, what type of topography do they form on. What's the difference between an area that's very barren and an area that's got tons of life? We're trying to figure that out. But also I can tell you right now, this is a quick analysis right here, and I did this for some other presentation a number of years ago, the second to last slide, is that here is just looking at counts per minute of animals that we recorded on a subset of those dives between the depths of 1,000 and 2,600 meters. And when you take a look at this, then you'll notice a couple of things. First of all, there weren't that many animals in the 1,000, 1,200 meter range, because that's getting into something called the oxygen minimum zone, we believe. But we didn't do that many dives anyway in this area. But the other thing, the other pattern is once you get down to around 2,500 meters, the abundance of animal drops precipitously. And it was noticeable to a point where then we started doing dives specifically targeting this phenomenon, and it held up. There is some environmental boundary at 2,500 meters that we do not understand what it is, but once you get below that depth, then you don't see these very huge, highly abundant, dense communities anymore. Okay, so what does that tell us? That is a valuable piece of information, because that means, can we convince the crust mining industry when they get started to perhaps mine below 2,500 meters and avoid the most spectacular communities that are down there? If they would be willing to do that, then perhaps this could work without too many environmental consequences. And finally, we're the custodians of an absolutely beautiful, amazing world. And I hope we can learn to utilize all of its resources, all of its wealth, without destroying it, extracting things sustainably. And with that, thank you very much.